So isotopes. Isotopes, there are atoms of the same element with different number of neutrons. You know the atomic number is the number of protons, which is equal to the number of electrons if it is neutral. But in the same atom or the same element can have different neutrons. It means the atomic number is the same, but the mass number can be different. If atomic number is different, there are two different atoms. But there can be atoms of the same element with same atomic number, but the mass number is different. Due to that difference, neutrons are also different. Number of neutrons are different. Now, for example, isotopes of hydrogen. There are 3 isotopes: protium, deuterium, and tritium. Here you can see clearly these 3 isotopes of hydrogen. Now their atomic models are given: protium, deuterium, and tritium. Their atomic number is 1. Z is 1. Therefore, protons, number of protons, 1. Number of electrons, 1. But in protium, deuterium, and tritium, the neutrons are different. The neutrons are different. Electrons and protons are the same, but neutrons are different. That is the idea of isotopes. In isotopes, the atomic number is the same, but the mass number is different because the neutrons are different. Atomic number 111, mass number 1, 2, 3. You can remember the equations for mass number. Here, mass number is equal to number of protons plus number of neutrons. From here, we know the equation. Mass number is equal to number of protons plus number of neutrons. With that knowledge, we can calculate the mass number in protium, deuterium, and tritium. The equation is mass number equals protons plus neutrons. A equals N plus P. A equals neutrons plus protons means the atomic number. So according to that equation, we can calculate the mass number. In protium, it is 1 plus 0 because 0 neutrons. It means 1. In deuterium, mass number is 2. How is that? Protons plus neutron. 1 proton plus 1 neutron. 1 plus 1, 2. In tritium, 1 plus 2, 3. So there can be questions to calculate mass numbers if you know the number of protons and number of neutrons. Even if you don't know the number of protons, if you are given the atomic number, that is equal to number of protons and number of electrons. So how to represent these isotopes of hydrogen? Hydrogen 1 1. Hydrogen 1 1. Hydrogen 2 1. Hydrogen 3 1. So the above number is the mass number. The below number is the atomic number. So if you are given the symbols and the standard representation, you should be able to write the number of electrons, number of protons, number of neutrons. Then chlorine, another example. Chlorine, now there are 2 isotopes in chlorine, here and here. Chlorine 3517 and 3717. Now if you are asked, if you are given these, what is the atomic number? Atomic number is 17. What is the number of protons? 17. What is the number of electrons? 17. What is the number of neutrons? Then you have to do a calculation for 2 different isotopes. How to do that? A equals P plus N. Number of protons plus number of neutrons. So, you know, the mass number is the above value, 35. Number of protons, you know, that is equal to the atomic number, or Z. This is equal to Z. You know, that is 17 in the first isotope. You can calculate the number of neutrons from this equation. N equals 35 minus 17. Okay, 35 minus 17. That is 18. So 18 neutrons. For the second isotope also, we can do the same calculation. A equals P plus N. A equals 37. P equals 17. N. N equals 37 minus 17 equals 20. So this says that the number of neutrons are different. First one 18, second one 20. So this is a good example for another isotope. Chlorine gas has these 2 isotopes. But these isotopes are not in equal amounts in the chlorine gas. Chlorine gas does not contain C35 and C37 in equal amounts. There is a percentage, that is the percentage abundance. 75% of the isotope is 35. 25 is 37. This is called the percentage abundance of the isotope. Percentage abundance of the isotope. That is about the isotopes. Then we want to discuss the patterns of the periodic table. Now the periodic table, there are physical and chemical properties of elements. They have a systematic pattern. You know the periods, you know the groups. Now, you know the rows and columns. To study these patterns, these properties should be specially considered. The first, ionization energy. You should know what is the first ionization energy. Also, you should know what is electronegativity. First ionization energy we'll first discuss about first ionization energy. Now, according to the nuclear models, you know the nuclear models now. You know the atomic models now. Nuclear model, planetary, Bohr model. Now, according to the nuclear model by Rutherford, electrons are orbiting around the nucleus. Electrons are negatively charged and they are attracted by the positively charged nucleus. Nucleus is positively charged because of the protons. Now, during a chemical reaction, you know, either removal of electrons occur or acceptance of electrons occur or sharing of electrons. Now, to remove an electron from an atom, energy should be supplied because there is an attraction between the positively charged nucleus and the electron. Therefore, a considerable energy should be supplied to remove the first electron. So if the first electron, if one electron is removed, it becomes positive. It becomes a cation or a positive ion, plus one ion. So the first ionization energy of an atom, of an element, is the minimum energy that should be supplied to an atom in the gaseous state to remove an electron to form a unipositive gaseous ion. You should remember this definition very clearly. The first ionization energy of an element is the minimum energy. The minimum energy that should be supplied to an atom in the gaseous state. The atom should be in the gaseous or gas state to remove an electron, one electron, to form a unipositive ion, plus one ion. That definition is very important. The formation of a unipositive gaseous ion by removing an electron from an atom in the gaseous state can be represented by this equation. For example, we'll consider sodium atom. Now sodium atom is in the, now it should be converted to the gaseous state because sodium is a solid. Sodium gas removing one electron forms sodium plus one ion. So that is the first ionization energy of sodium. then this energy is comparatively small value for an atom. Therefore, this value is given for, now if you consider one particular atom, this first ionization energy is very small. Therefore, what we do, we consider a large number of atoms, like 0.6.002 into 10 to the power 23 number of atoms. That is known as a mole of atom, because one mole is equal to this number, that is known as the Avogadro number. This number is known as the Avogadro number. Avogadro number. So, if you consider that number of atoms, so the first ionization energy can be defined for 1 mole of atoms. So then the first ionization energy for 1 mole of sodium can be defined. Why we define it for 1 mole? Because one atom has a very negligible amount of first ionization energy. That is why we multiply it for a large number of atoms, or a mole of atom. You know, dozen means 12. 1 mole means this number, Avogadro number, 6.002 into 10 to the power 23. Mole is nothing new. 1 mole is like 6.022 into 10 to the power 23 number of atoms. 1 mole of atom. Therefore, first ionization energy can be defined for kilojoules per mole, not per atom. Kilojoules per mole. That is because if you define the first ionization energy for one atom, it is very small. Therefore, we want to define it for 1 mole. Now, in a given period, the group 1 elements have minimum first ionization energy. Group 8 elements have the maximum ionization energy. Also, from left to right in a row or a period, the first ionization energy varies in a regular zigzag manner. And also, this variation is valid for second and third periods in the same way. Now, first we consider group 1 elements. Now, you know the group 1 elements. You should know these patterns very well. Now, this first ionization energy variation against atomic number. Atomic number means number of protons. And you can see the atomic number. So, sorry, first ionization energy is defined as kilojoules per mole. This is the atomic number, or Z. You can see the variation here. You can see the variation here very clearly. This variation is very important. Atomic number and first ionization energy. Look at group 1 elements. They have minimum first ionization energy. Hydrogen, lithium, sodium, potassium. They have the minimum first ionization energy. It means very easy to remove the first electron from the group 1 elements. Then you can see another pattern. What is that? The maximum first ionization energy is in group 8 or noble gases. What is the reason for that? Their electrons are fully filled. They are stable. Very difficult to remove the first electron. First ionization energy is very high. Then from left to right, the first ionization energy varies in a regular manner. Also the third and fourth. You can see the variation. Hydrogen, helium, lithium, beryllium. Then beryllium to boron, there is a drop. Nitrogen to oxygen, there is a drop. So this zigzag variation is common for the second and third periods as well. So these are the periods. First period, second, third, fourth. So these patterns, you can compare these two patterns. They are more or less the same. Now in the exam, if you are asked with A, B, C, D, E, F, so you should be able to identify the atoms. If you are given the period, second period means this one, third period means this one. That is with your knowledge of the about the periodic table. This is the first period. This is the second. This is the third. This is the fourth. So that is about the variation of ionization energy. Now there are important details. Group 1 elements, the first ionization energy decreases from top to bottom of the group. That is also a clear observation. That is a clear observation from this. You can see that is hydrogen to helium. First ionization energy drops. Lithium to sodium once again drops. Sodium to potassium also drops. It means first ionization energy drops in the group 1 from top to bottom. From top to bottom in group 1, the first ionization energy drops. That is also a very important pattern. What is the conclusion of that? From top to bottom of a group, ionization energy decreases. That is for any group. It means the number of energy levels in an atom increases. Energy levels, the levels or shells that are filled with electrons increases when it goes down. It means the attraction from the nucleus decreases to the outer energy levels. So, electrons are easily removed. Now, in group 1, if you go down, hydrogen, lithium, sodium, potassium. Hydrogen, 1 energy level. Lithium, 2. Sodium, 3. Potassium, 4 energy levels are there. So if you consider the atomic radius, electron here is more attracted to the nucleus. But here the distance is greater, so less attracted. This electron is easily removed than this electron. That is why the ionization energy is low. Ionization energy is the energy required to remove this electron. So this attraction is less, therefore this is easily removed. Therefore ionization energy is lower. That is why the ionization energy decreases down the groups. That is why the ionization energy decreases down the group. Then the other pattern, the other property that you should know is electronegativity. Electronegativity means the ability of an atom, of an element, to attract the electrons of a bond towards itself when it is bonded to an atom of another element. Now, there are two atoms. When two atoms are bound together, there are electrons which form the bond. This is one. Now, if it is like atom A and atom B, they form a chemical bond with electrons. Now, the ability to attract these electrons towards a particular atom is known as the electronegativity. The attraction of an atom of higher electronegativity towards electrons is greater than that of lower electronegativity. If a certain atom is more electronegative, it attracts. More about electronegativity can be discussed under chemical bonds, that is about the covalent bonds. Now this electronegativity can be measured using the Pauling scale. Pauling scale. Pauling scale. According to Pauling scale, fluorine, F, capital F, is considered the most electronegative atom. Pauling scale does not give electronegative values to noble gases as they don't form chemical bonds readily. But using the Pauling scale, electronegativity can be compared. Now, if you go from left to right across a period, the electronegativity increases. If you go down a group, electronegativity decreases. It means, according to Pauling scale, from here to here, in a period, if you go like this, the electronegativity increases. If you go down a group, electronegativity decreases. It means more negative ions are formed this side, that you know. Sodium plus ions are formed, but chlorine likewise negative. That is due to this electronegativity difference. When you go down the group, positive, more and more positive ions are formed. So using the Pauling scale, we can compare the electronegativities of a group or a period. Now here, they have given the Pauling electronegativity values. Compare the Pauling electronegativity values: lithium 1, beryllium 1.5, boron 2, carbon 2.5, nitrogen 3, oxygen 3.5, fluorine 4. So electronegativity increases. Then go down a group: hydrogen to lithium to sodium to potassium. Hydrogen 2.1, lithium 1, sodium 0.9, potassium 0.8. Electronegativity decreases. This way it increases. This way it decreases. Here also you can see the electronegativity with the atomic number. Hydrogen to lithium, it drops. Then across the period, it increases up to group 7. You can see these patterns clearly. So that is the lesson today. Now you can stop recording.